My goal for today is to demonstrate that quantum physics is not only anti-intuitive, which is, but also practical, also useful. So I'm going to talk about some quantum stuff. Everything starts with the vacuum tube that brought electronics into existence during the early 20th century. They were amazing, they were great, but they had a lot of, they had several issues. They were big, and they generated a lot of heat, and also they broke quite easily. But still, they are used to this day. You may have heard that high-end sound equipment uses steel. It gives, they say it gives a warmth to the sound, and is using very expensive high-end sound equipment. Anyhow, drawing in quantum theory, AT&T invented a very good, an optimal almost substitute for the transistor, sorry, for the vacuum tube in 1947, which is the transistor, that enabled everything, that all the electronics like portable computers that we are using right now. This transistor triggered the so-called first quantum revolution that brought also other devices such as those atomic clocks, nuclear magnetic resonance, or also lasers. All this black and white stuff works thanks to quantum effect, okay? But they are noisy. They are noisy in the quantum sense because they do not really exploit the richness, let's say, of the quantum realm, of the quantum effects. But all that changed with the work of John Stewart Bell and others in the 60s of the previous century on quantum entanglement. Okay, this is a quantum effect whereby two or more particles cannot be described independently, but rather as a bound set. We say they are strongly correlated, which, by the way, led to the Nobel Prize in Physics last year, this work and the experiments that proved that Bell's theorem are real. The universe behaves like that. In short, Bell's and these guys' works sparked the so-called second quantum revolution, which is the one we are now, which is characterized by the possibility of controlling the state of individual particles. And well, this has in turn enabled several quantum technologies, such as quantum metrology, simulation, computing, and the coveted quantum internet. And I'm going to talk a bit about this four. So starting with quantum metrology, this is a series of techniques that make it possible to improve measurements through quantum effects, typically through the famous quantum entanglement. One excellent example of this is PET, positron emission tomography, which is an imaging technique that uses amazing phenomena. It goes by making use of matter, antimatter positrons and electrons, annihilation that creates a pair of gamma photons which are entangled. And so a ring of detectors around your head detects those two photons, and they can correlate where and when exactly they were, the matter-antimatter annihilation took place. The thing is that this quantum metrology in general can measure stuff with a very, very tiny number of particles and energy, and so without virtually without altering the sample. Okay, so it makes these techniques suitable for being used in vivo, in biological tissues. So quantum metrology is not very well known, but it offers really a lot of practical applications which are starting, and in my opinion is one of the most promising quantum technologies for the coming years. Let's move on to quantum simulation. This is about considering very complex systems, for example, a black hole, okay, and rather than modeling it as usual we do in physics with a mathematical model and lots of complex equations, we use instead an analog quantum system. And instead of studying the math, we do study the real physical system. In this case, for a black hole, the quantum analog is a superfluid. Okay, this is really, really interesting for the actual scientific stuff, but I don't see this having an immediate impact on everybody's lives. But what about quantum computing? Okay, this is a big one. Quantum computing is nothing like classical digital computing, so I'm going just to scratch the surface in a few minutes using a metaphor that I've come up with that, well, as all metaphors, it's incomplete and in some respects sometimes somewhat misleading, okay? But I hope it will at least open a window to you on what quantum computing, quantum computers are. And I'm going to use a metaphor based on images. Let's see. So, digital computers use bits. Everybody knows that. The minimum amount of information, black or white, 0 or 1, up or down. If we want to represent the Mona Lisa with 1 bit per pixel, it will look this bad, okay? We only have full blacks and full whites, and we get this sad picture of the Mona Lisa. Quantum computers, on the other hand, use qubits that stand for quantum bits that are in practice realized with tiny, tiny stuff, such as this example, trapped ions, superconducting loops, or quantum dots. Quantum dots that, by the way, have led to the Nobel Prize in Chemistry this same year, just a couple of months ago. Now, on top of the normal basis states, we call them states ket 0 and ket 1. Ket is the name for these funny symbols which have a lot of science behind. Just forget it. It's ket 0 and ket 1. On top of those two, the thing is that qubits can be in intermediate states, okay? Thanks to another quantum phenomenon, which is called the quantum superposition. Phenomenon which is very badly known due to the infamous Schrodinger's cat. Spoiler, cats are far too big and far too hot to manifest quantum properties. So the metaphor of the quantum of the Schrodinger's cat was used exactly on the opposite sense that it was intended for. Complete cats cannot be in quantum superposition. They are represented, these superposed states with this diagram in the shape of a sphere. Let me get the cursor. Okay, this sphere is called the Bloch's sphere, and the arrow, the vector, points to any point in the sphere representing this superposition. The thing is that every state is a linear combination of the basis ket 0 and ket 1 states using as coefficients complex numbers. The thing is that with this possible variation around the Bloch's sphere, a quantum bit, a qubit, can represent any shade of gray, more than 50 actually. So in our metaphor, our Mona Lisa using qubits will look this good. Now, what if we have, for example, 3 bits? Bits are independent among them, so 3 bits can give rise to 8 distinct colors. So if we use these 8 colors to represent a bucolic pyre in a bay, the resulting image will be something like this, quite lurid, if you ask me. But what happens with 3 qubits? With 3 qubits, we can represent, using superposition, any shade of the 8 basic colors. So we are already doing better, but we have more. Now we can exploit the quantum entanglement effect that we saw earlier, and somehow mix together all these shades of colors, resulting in any color that we can think of, thanks to quantum superposition and quantum entanglement in this metaphor of the pictures. So now this massive set of colors will do justice to our picture of the pyre, which will result this good. Okay. Manipulating a set of entangled qubits change the state of all of them, let's say, in parallel. Okay, and this is one of the key factors that make quantum computers, that enable them to do things that are simply impossible, are completely out of reach for classical digital computers. In this sense, it is said that the computing power of a quantum computer with n qubits is equivalent, in a sense, to that of a digital computer with 2 to the n power of bits. And you know how the exponentiation goes. It grows very fast. So if we will have 266 qubits, which is a moderate number, that will be equivalent, a computer with those qubits will be equivalent to a digital computer with 10 to the 80 power bits. And that's a massive number. That's actually bigger, it's larger than the number of atoms in the observable universe. Now, there is a gotcha, there is an issue. The fact that when we want to obtain the result of a quantum computation, we need to perform what is called, in quantum theory, a measurement. We need to measure the quantum system, and we force the collapse, it's called the collapse of the wave function. And this has two effects. First, the entanglement is destroyed. So all qubits become independent. They go to the classic realm, if you want. And second, each qubit is projected onto the base that we select for the measurement. So the act of measuring implies an effect on the thing that we are measuring. And the probability that we get one result, one basis or the other is actually proportional to the square of the coefficient that we saw earlier on that was representing the complete entangled state. In short, after these 3 or 4 sentences, quite arid, when we do open the box, we realize the cat, which was in superposition, we realize it was actually alive or dead, whatever the case. Now, what happens with our good-looking picture? This good-looking picture was like that inside the quantum computer, but when we bring it to the classical realm, when we measure it, all these colors collapse to the 8 base ones, to the ones represented by the bits. And so the final image we will obtain in a quantum computer will be like that. That image at the right, which is the third, is using only the 8 colors that the one at the left. But it really looks better, doesn't it? And that's because we have obtained this image not by processing the pixels one by one, by looking at all of them at the same time. Okay, that's my metaphor for what the power of a quantum computer resides on. So let's summarize. What is a quantum computer? We can describe it as a set of qubits which are capable of being in superposition and also entangled among them. And here comes the magic, of course. We make them interfere, that's the difficult part, inside the quantum computer using a quantum algorithm. And the goal of that quantum algorithm is to maximize the amplitude of the state, which is good for us, is the result we are looking for in the computation. We manipulate the superposition so that there is a larger coefficient for that state, so that when we measure, we have a high chance of obtaining the result, the answer that we wanted, which of course is always 42. So the difficult part, the magic, where magic happens is in the algorithm itself. I don't have a lot of time to go in details, but quantum algorithms are a thing of beauty, and I recommend you read about them. Fourth thing we want to cover, quantum internet. Okay, this is a theoretically unhackable communications network which uses quantum stuff. That, by the way, doesn't exist today. It will use quantum cryptography for security. And there, in quantum cryptography, we do have some elements, some bricks for building the quantum internet. And the first one I want to talk is quantum random numbers. Random numbers are actually not only important in cryptography, but also for many, many scientific activities and also for engineering tasks. Look, the first edition of this book was published in 1955, if I remember correctly. And yes, it is what it says. It's 1,000,000 random digits, a book with 1,000,000 numbers, one after the other, obtained using a roulette wheel. It is sold in Amazon. You can look for it. And it has very funny, very, very funny reviews. It's hilarious, some of them. But you know, digital computers are deterministic, okay? And that's why they are terrible at inventing, let's say, random numbers. The most digital computers can do is generate pseudo-random numbers using an actual algorithm. I remember when I was doing my PhD, a long time ago, we couldn't trust the libraries for computer numbers that come with the computer, and so we coded our own algorithms. This one is mine, is based on one in the book Numerical Recipes that the ones with gray hair may remember those books. Okay, today the machines, even the ones you have in your desk, are much better. For example, the dev random device in Linux adds entropy from the environment. In particular, it uses the time between two successive keystrokes or other sensors that the computer may have to generate better random numbers. Now, there are companies that provide random numbers as a service. You can pay them for giving you random numbers. And this one is funny. It's called LavaRand and uses as entropy source a bunch of actual lava lamps that they have in the company's lobby. So they have a webcam looking at the hues of the lava flowing, which behaves as a chaotic phenomena, and so is a good source for entropy for random numbers. Now, today, there are chips that measure internal quantum processes within the chip, and that way they do generate true random numbers that are used in lots of activities, such as network routers, medical implants, and also in cryptography, as I will explain later. This one actually is a model, is a very high-end one. It generates gigabits of random digits per second, and we are actually using it in a project that I will talk later. Another piece of this future quantum internet we have already developed is the distribution of cryptographic keys by quantum means, or QKD. So imagine two persons, Alice and Bob, want to have a common key for sharing secrets afterwards. There are actually two types of QKD protocols. I'm going to describe the easiest to understand, which is BB84 by its authors, Bennett and Brassard, and the name. And the metaphor I'm going to use this time is an actual roulette wheel. So Alice spins the wheel and she gets a black 17. She spins again and she obtains a red 23. And yet again, and in this case, she gets a 28 black. Okay, she does this as many times as bits she wants in the final key and derives the bits from the parity of those throws. So 1, 1, 0, 0, 1, etc. Now, the next step is that Alice takes the first complete throw, the 17 black, and sends that to Bob. Now, what is this 17? Well, this is an actual quantum system, okay? Might be a photon whose quantum state is encoding the parity, the thing she wants to transmit, but in one of two conjugate bases, which I'm representing in this metaphor with the color, either the black basis or the red basis. So both the parity and the basis, the color, are random because we have obtained them from the roulette wheel. So now Bob takes that throw and selects at random again the color of the glasses that he is going to use to read that quantum state. Okay, so she selects at random black glasses, looks at the quantum state, and derives the fact that it's even. So he gets a 1. Similarly, for the second throw, he has selected red glasses and derives, which is also a 1. What happens in this case? For the third bit, Alice sends a quantum state, which is using the black state, the black basis, but Bob has selected for reading it red glasses, so that's incorrect. What happens in this case? Well, the quantum state in the red basis is not a basis state because it's encoded using the black basis. It's a superimposed state in that basis. So when Bob measures that state using its red glasses, remember with the image before, the state collapses onto a basis state, one of the two, in the base he's using, which is the red one. So what are we going to get, a 0 or a 1, an even or an odd, provided the throw was black? Well, that's the interesting thing. We are going to obtain a random result. That's how the universe behaves. It's not my fault. So when Bob derives the parity of that third bit, he gets a 1, which is of course incorrect. Anyhow, he does this for all bits in sequence. And now the thing is that Alice and Bob call each other using a phone, okay? Using any classical communication channel, and they share what color bases they have used. Alice for preparing the throw, and Bob for measuring it, okay? So they go like, okay, I've used black for the first, and you, me black as well. Okay, we have matched our base colors, so the bit that Bob has obtained is good. What with the second, red and red? Good, we are doing good. We can also trust this bit. What about the third? Oh, too bad. Okay, Alice used black, Bob used red. We cannot trust this bit. We cannot trust your measurement, Bob, because you have done it at random. So we need to discard this bit, okay? And they do this for all the bits in the message. They discard the ones for which the bases selected at random didn't unfortunately match, and the final key shared by them is 1101. Why all this complexity? Because we can, okay, what's the probability of matching between the bases? The colors are selected at random, so the probability of match is 50%. Half of the bits are lost in the process. Why we do this? Because we can have an evil Eve, okay, a person, a bad guy, a bad girl in this case, eavesdropping the channel. So let me explain how this behaves. Let's go back to this situation. Alice sends the 23, which is intercepted by Eve. So Eve reads it with glasses whose color is selected at random. She selected red in this case, and she deduces that bit to be a 1. Now, Eve can create a new quantum system which is congruent with the value and the information she has. So she creates a 23, for example, even and red, and she forwards that to Bob. Bob uses the red glasses, and he derives also a 1 for this bit. So doesn't look we have done much. Huh? It will seem that we have actually achieved nothing because Eve has got the 1 and nobody has realized. But here comes the beauty. There is something very interesting, and it's the fact that this 50% of matching between the bases that we have at the beginning is now realized in between Alice and Eve. Eve is selecting its bases at random, so there is a chance, a 50% chance that Eve selects the one that was used by Alice. And in the same way, there is a 50% chance that Bob uses the basis selected by Eve. So when Alice and Bob talk over the phone, they are going to realize that the matching between their bases is at 25%. They do this by exchanging some actual measured bits, okay, that get discarded. There is a bit more behind under the hood that I'm not explaining. The thing is, they will know for sure at all that the channel is compromised, and so they will not use the key. They do know that the channel, that someone in the middle has been tampering with their photons of whatever. Is in the sense that quantum key distribution provides what it's called perfect secrecy. And this is guaranteed not by our smart brains, which is also a component, but due to the quantum mechanical laws of the universe. Okay. In practice, quantum key distribution is performed by encoding photon polarization, which is the parity, if you want, of my previous example, on either perpendicular directions of the polarization or the phase of the optical fiber. Anyhow, the thing is that the delicate quantum nature of the signal over the optical fiber limits the range, and it's currently around 100 kilometers. So you need to install secure repeaters every 100 kilometers if you want to communicate via QKD to people or to buildings or to centers that are far away. Europe is actually building one of these QKD networks. It's called the European Quantum Communications Infrastructure, EuroQCI. And at Madrid, we do have like an embryo of this, of what we want to connect to EuroQCI, and this is the current map. But by far, the longest QKD network in the world is in China, with 2,000 kilometers of already working network between Shanghai and Beijing, with almost 50 nodes between them. Now, it's a nuisance to have secure nodes every 100 kilometers. Longer distance could be achieved if we got rid of the solid material of the fiber optics. Is solid, is bad for transmitting light. What if we do transmit through air, or even better, through space? Okay, and that's what we like. We like space, and that's actually been also done by China. So they are quite advanced in quantum technologies, which are prototype with a satellite, which they have called, the name of the program is Quantum Experiment at the Space Scale, QUESS, and it's has been able to transmit, to perform distillation of cryptographic keys between Beijing and this Urumqi thing or city, which is near the border of Europe already. Moreover, they did a test, a single test, which was actually too successful between Beijing and Vienna, and Vienna is already at 7,400 kilometers. So that's a noticeable distance. This satellite, the actual satellite, is called Misius in honor of the Chinese philosopher Mozi of the 4th century before the Common Era, who, among other things, studied the properties of light. Okay, ESA, the European Space Agency, is launching next year, hopefully, a satellite, a LEO satellite, which is going to do something quite similar to the Chinese Misius, which is going to be called Eagle-1, and whose satellite control center is being done at GMB. This is also a prototype, okay? But if the Chinese have Mozi, we do have Juan de Caramuel, a gifted man, Spaniard, born in 1606, sometimes called the Spanish Leibniz, and who, among many other things, studied cryptography and actually devised the binary system, which was later plagiarized by Leibniz. So next time someone asks you who is the inventor of the binary system, is Juan de Caramuel, Spanish guy. And so we have used its name in his honor, Caramuel, in a study for QKD using a geostationary satellite that we have performed in the last couple of years with a consortium made of many Spanish organizations and companies, all of them Spanish, including GMB, which is the responsible of the ground segment. Now, this study was performed and is now being considered to be used, this quantum key distribution through geostationary satellites, for IRIS², the future European infrastructure for resilience, interconnectivity, and security by satellite. And now, given the fact that Copernicus and Galileo are two of the big European satellite programs whose names are come after two great European scientists, Copernicus and Galileo, I wonder, couldn't we get rid of this horrible IRIS² name and call the constellation Ramón y Cajal? Okay, that's my proposal, and I hope this may come true sometime in the future. Cajal constellation, I dream of that. Okay, very quick, some takeaways. First, your universe is quantum, okay? If you don't feel it, the culprit is you because you are too big. Okay? Quantum technologies are with us today. I will say that genome edition and quantum stuff are the two technologies that will have the greatest impact on our society in the next decade. Okay, after that, we hope fusion energy may play a big role, but it's not coming in 10 years. So my bet is genome editing and quantum technologies, in particular quantum computers and quantum metrology. And finally, quantum computing. Quantum computing will undoubtedly revolutionize how we deal with certain problems, but quantum computers are not going to make your Excel faster, are not going to increase the frames per second that you get when playing Minecraft. It's only useful for certain specific tasks. And I think this is all. This concludes my presentation. So thank you very much for your attention.